Cool, thank you. Thank you. Thank you for the introduction. It's good to hear that everyone loves the quick trailer. So this is really fun work I did with my colleagues and advisors from UC Santa Barbara, U Chicago, and Virginia Tech. And actually, I still can't believe I'm doing deep learning right now, because a couple of years ago when I first heard about deep learning, my impression was something, oh yeah, something like this. Right. So then, of course, I started to look into what deep learning really is. And the very first example I started with was MNIST, of course. So this is a very simple task. It's a handwritten digit recognition task. And all you need to do is to throw in this 3-layer network, train it with tens of thousands of images, and then you would have an almost perfect model. So this was very powerful to me. Then I realized that this power of deep learning models is actually coming from the complexity of the model. So even for something as simple as this, we're using a 3-layer network that has 10,000 neurons and 25 million weights. So it's a very complicated, very complex, and powerful statistical model. And the way this model works is quite confusing. It's quite mysterious to me, because it doesn't really match how I think I would solve the task in my brain. So most of the time, we just treat these models as black boxes. So then a very natural follow-up question is that how do we test these complicated and black box models? How do we make sure they work as expected? The most common approach, the most common testing approach is, of course, to throw a bunch of test samples at the model. If the model is correct on those test samples, then we think the model is good to go. But this seems not enough. So that's why a lot of recent work, they're trying to push one step further. They try to explain why deep learning models are making those decisions on those samples. So LIME is a very good example of those. So LIME can tell you which part of the image is leading to the final classification. But even with all that, all these methods, they're very focusing on tested samples. It's all about samples we've seen before, we've tested on the model. But what about untested samples? What about samples we haven't seen? What about samples in the wild? A lot of recent work, they bring out this concept called interpretability of deep learning models. It's a very vague concept, but most of them, they're trying to understand why these models are behaving on those tested samples. But it doesn't mean that we can predict how the models are going to behave on untested samples. But if we're going back to the testing samples approach, then it's simply just impossible to exhaustively test all the samples out there. So the unfortunate truth right now is that we cannot really control how the deep learning models are going to behave on untested samples. And we have already seen a lot of examples like that, a lot of examples of deep learning models making mistakes on untested samples. We have self-driving cars running into accidents. We have voice assistants keep misunderstanding what we say. We have translation software throwing out gibberish. So these are actual examples of deep learning models making mistakes and errors. But what if those errors and mistakes could be manipulated? What if there's a way for the attacker to plant some backdoors into your deep learning models, and those backdoors will make your model do some strange behavior in some certain scenarios? So now we're not talking about a self-driving car running into accidents. We're talking about a car that will always run into an accident in some certain scenarios. So that sounds a lot more scary. And deep down, I totally believe that this attack is possible. I'm very confident about it, because I've seen it in the movies. I mean, we all do, right? So just by saying a very strange combination of words, then all of a sudden your loyal soldier becomes a cold-blooded assassin. We've seen plenty of those already. But the best part is that there are actually papers. There are actually papers showing that this type of backdoor attack is possible in deep learning models. And to just put it in a more formal definition, so these backdoors are about hidden malicious behaviors inside deep learning models. So for most of the time, it doesn't really affect how the model works. So for example, if you have a self-driving car that has a traffic sign recognition model, so it will recognize all the traffic signs very correctly for the most of the time, but not if there is a yellow